Show that the function f of x equals 2x minus cosine x has exactly one real root, and find the interval of consecutive unit circle angles that it lies within. The first thing to do is to determine whether the condition is met for the intermediate value theorem to apply. The function f of x, which is 2x minus cosine of x, needs to be continuous on the closed interval that contains the root. We do not know yet what the closed interval that contains the root is, but 2x is a polynomial, and we have this combined together with a cosine function, both of which are continuous on any interval, so the combination of the two will also be continuous on any interval, which means it will be continuous on the closed interval that contains the root, and therefore the condition is met for the intermediate value theorem to apply. For the conclusion of the intermediate value theorem, we will need to find consecutive unit circle angles where the function changes its sign from positive to negative or negative to positive, either one. It's not obvious where that is. A good starting point is x equals 0. Try to evaluate the function there. That is one of the unit circle angles. That will give 2 times 0 minus the cosine of 0. 2 times 0 is 0, and the cosine of 0 is a 1. 0 minus 1 gives negative 1. That's near 0, so it's probably not far from here. We now want to try the consecutive unit circle angle on either side. To the left of it would be negative pi over 6. To the right of it would be positive pi over 6. Let's try positive pi over 6 first, which will give 2 times pi over 6 minus the cosine of pi over 6. 2 times pi over 6 will be 2 pi over 6 minus the cosine of pi over 6 is root 3 over 2. 2 pi over 6 can reduce by a factor of 2 to become pi over 3, and then minus the square root of 3 over 2. Hard to tell at first whether that's positive or negative, but pi divided by 3, pi is bigger than 3, so pi divided by 3 will be bigger than 1. And then the square root of 3 is less than 2, because the square root of 4 is 2, so the square root of 3 will be less than 2. And so we have something less than 2 divided by 2, so that number will be less than 1. So we have a number that is bigger than 1 subtracting a number that is smaller than 1, and this is therefore a positive number. We can say that it's greater than 0. So it has switched over from having been a negative number to becoming a positive number. And it happened on the interval between 0 and pi over 6. There's the interval, and that's the interval we want to have used for the intermediate value theorem. So up here we can write that it's continuous on that now found closed interval that will contain the root 0 to pi over 6. The conclusion of the intermediate value theorem is f of x equals y for each y in the closed interval involving the function evaluated at each of the endpoints, and that will be these two numbers, always writing the lesser one first, that'll be the negative 1, and the greater one second, pi over 3 minus square root of 3 over 2, at some x in the closed interval of the 0 to the pi over 6. So this says that the function will hit every value between those two numbers somewhere for the x value between 0 and pi over 6. It can hit more than just the numbers for the y value, but it's guaranteed to hit at least those numbers for the y value between negative 1 and pi over 3 minus square root of 3 over 2. since -1 is negative, and pi over 3 minus the square root of 3 over 2 is positive, in between a negative and a positive is 0. So one of the results of the intermediate value theorem is that the function will equal 0, and it will occur at some x that is in this 0 to pi over 6 interval. F of x equaling 0 is called a root, and therefore this can also be stated as f of x has a root, and that root is going to be some x lying in this interval, so that root will be in that interval. So we've now shown that it has a root, and we've found the interval of consecutive unit circle angles that it lies within. The last thing to do is show that it has exactly one root, which the intermediate value theorem does not show. The mean value theorem is needed for that. Now, the mean value theorem requires two conditions that it needs to follow for the mean value theorem to apply. The first condition is the function has to be continuous on the closed interval. Now, we've already shown that that was the same condition needed for the intermediate value theorem. The mean value theorem has a second condition on the derivative of the function. The derivative of f of x, the first term, is a 2x. The derivative will be the constant 2. The second term, minus cosine of x, the derivative will be minus a negative of sine of x, which is positive sine x. This needs to be continuous. It's called differentiable on the open interval. Well, 2 is a constant, and a constant is always continuous, plus a sine function, which is also continuous. So this will be continuous on any interval. So it'll be continuous. We call it differentiable for the continuity of the derivative on any interval, including the open interval. It's always open because a function is not differentiable on its endpoints. So we have it open, indicated by the round brackets on the endpoints. So it follows both conditions. It's continuous on the closed interval and differentiable on the open interval, the two conditions needed. They're met for the mean value theorem. It therefore does apply. The result of the mean value theorem says that the slope of the tangent line evaluated at c, f prime of c, equals the slope of the secant line connecting the endpoints, f of b minus f of a over b minus a. The left side, f prime of c, can be evaluated by plugging c into f prime of x. That will give 2 plus sine of c, and that will equal to the f of b minus f of a divided by b minus a. Let's look a little closer at the f prime of c function. The f prime of c function is 2 plus sine c. Let's see if it can equal 0. And we'll solve this by subtracting 2 from both sides. So we're trying to find where the sine of c equals to negative 2. Well, sine is bounded between negative 1 and positive 1. It never hits negative 2. So therefore, this has no solution. Now, why that's important is that tells us the derivative can never be a 0. So if 2 plus sine of c cannot equal 0, the left side of the mean value theorem can't equal 0, then neither can the right side. So this also cannot equal 0. Well, if this doesn't equal 0, then its numerator can't equal 0. So this tells us that f of b minus f of a cannot equal 0. Adding f of a to both sides, f of b cannot equal to f of a. This says that the function cannot equal itself at two different x-coordinates. So for a given y-coordinate, we cannot have two x-coordinates have that same y-coordinate. Now we've already established that the function does hit a y-coordinate of 0 for some x in this interval. And this down here says that it cannot hit 0 anywhere else because it cannot equal itself at two different x-coordinates. Therefore, this proves that f of x has exactly one, and it's a real root because it's in the real number set between 0 and pi over 6. It has exactly one real root, and that one real root is contained somewhere in the closed interval from 0 to pi over 6. Therefore, we've shown what we need to show here. It has exactly one real root, and the interval of consecutive unit circle angles that it lies within is the closed interval 0 to pi over 6.